Hey, what's going on, everybody? It's day 14 of Advent of Code 2024. We're about to dive in here, 3 minutes and 45 seconds, and look into the problem a little bit further. I've got my day 14 already stubbed out, and we're ready to go. So as you can see here, everything's running fine. Little comment on yesterday. I did struggle quite a bit on day 13. Turned out it was a math problem. Approached it a non-successful recursive call way. Initially, stack was pretty deep. Went Dijkstra, solved part one, but part two is terribly more complex, and it turns out we could just solve it with math. So I've kind of refreshed myself, understand a little bit better the approach there, and we'll see what today brings. Thanks, Ronnie. Appreciate it. Hopefully, well, we'll see what the approach is today. I think one of the things I need to do with these, as I refine myself a little bit more, is really take the time and understand the problem instead of hacking away at it so quickly. I think had I paid more attention yesterday to what my initial implementation, I would have realized it was a poor solution before I even started, and would have went with solution number two, which still wouldn't have solved part two. But then at least I could have been much further down the road faster. So we'll see how today goes. What was it, Ronnie? You said, are you working with Golang right now? Is that true, or were you looking at Rust? I can't remember. I talked with a couple people the last couple of days, and be honest, quite tired. I live on the East Coast, so this is midnight for me. So doing that multiple nights in a row, and getting up at 7, 8 o'clock in the morning to do my 9 to 5 has been a bit exhausting, but it's okay. It's all in good fun. Yeah. Okay. Cool. Yeah. One minute. Yeah, I just changed the configuration on my ZSA keyboard. I have the ZSA Voyager, and one of the things I didn't like is by default the tilde or the backtick key was on the second layer, and then to access the tilde you had to go to the second layer and then going further. And so I've adjusted some of my keyboard layout, trying to make it a little bit more efficient to use. So some of my typing mistakes are just from having a completely different keyboard layout. Kind of talked about it before, but this is my keyboard here that I use. Except I have a black one instead of white, so it's a split layout. And then it's columnar, so that's another challenge. But then also, like, your standard special characters aren't in the normal places, and so they use something called layers to access those. But we got 9 seconds here, so let's dive in. 3, 2, 1. Day 14. Restroom readout. Out of this, one of the historians needs to use the bathroom. Fortunately, there's a bathroom near an unvisited location on their list. And so you're all quickly teleporting directly to the lobby of Eastern Bunny headquarters. Unfortunately, EBHQ seems to have improved bathroom security again. After your last visit, the area outside the bathroom is swarming with robots. To get the historian safely to the bathroom, you'll need a way to predict where the robot will be in the future. Fortunately, they'll all seem to be moving on the tile floor in predictable straight lines. You make a list, your puzzle input, of all the robots' current positions and velocities. One robot per line, for example. B equals 3 minus 3. Okay. Each robot's position is given as a XY, or P equals XY, where X represents the number of tiles the robot is from the left wall, and Y represents the number of tiles from the top wall when viewed from above. So a position of P equals 0, 0 means the robot is all the way in the top left corner. Each robot's velocity is given a v equals xy, where x and y are given in tiles per second. Positive x means the robot is moving to the right, and positive y means the robot is moving down. So velocity of 1 minus 2 means that each second the robot moves 1 tile to the right and 2 tiles up. The robot outside the actual bathrooms are in a space which is 101 tiles wide and 103 tiles tall when viewed from above. However, in this example, the robots are in the space which is only 11 tiles wide and 7 tiles tall. Okay. The robots are good at navigating over under each other due to a combination of springs, extendable legs, and quadcopters, so they can share the same tile and don't interact with each other. Visually, the number of robots on each tile in this example looks like this. Okay. So we've got 0, 1, 2, 3, 4. Okay. Okay. These robots have a unique feature for maximum bathroom security. They can teleport. When a robot would run into an edge of the space they're in, they instead teleport to the other side, effectively wrapping the edges. Here's what the robot P2, 4 v equals 2 minus 3 does for the first few seconds. Okay, after 2 seconds, after 3 seconds, after 4 seconds, after 5 seconds. Okay. Because it teleports to the other edge. Okay. Okay. And then over here. Okay, cool. Got it. The historian can't wait much longer, so you don't have to simulate the robot for very long. Where will the robot be after 100 seconds? In the above example, the number of robots on each tile after 100 seconds has elapsed looks like this. To determine the safest area, count the number of robots in each quadrant after 100 seconds. Robots that are exactly in the middle, horizontal, vertical, don't count as being in any quadrant, so the only relevant robots are exactly in the middle, horizontal or vertical, don't count. Sorry, what? The number of robots that are exactly in the middle. So the middle row and middle column? Is that what it's saying? Don't count? Yeah, okay. Example, the quadrant contains 1, 3, 4, and 1 robot. Multiplying these together gives a total safe factor of 12. 1 robot. Okay. 3 robot. 4 robot. Okay, 1. Okay, so we count the number of robots in each quadrant. Got it. Predict the motion of the robots in your list within a space which is 101 tiles wide and 103 tiles tall. Which will the safety factor be after exactly 100 seconds have elapsed? Okay. So let's look at our puzzle input. Let's see if we can get some additional thoughts here. So, well, yeah, maybe. Um, I think the answer is that we know we can well, I'm sure each of these points are going to have some level of predictability so that as we process a given point, at some point we may come back to a point that we've been at before And we know that at that point, in that processing for that point, I might be over optimizing it right out of the gate. Well, we've only got, how many inputs are we talking about here? So I suppose for like phase one, it's not that big of a deal. We've got 500 inputs and we've got to move 100 iterations for 500 of these inputs. And all we have to do is figure out where they are. But it's not just math because, well, it could be, maybe I'm not a math expert, but we can solve this without math. The challenge is whenever we go off the map, we have to wrap the map, right? So if we exceed 101 and 103 tiles wide, we have to wrap back up the map. And so I just wonder if after 5 seconds, let's get our test input. And let's think about this for a second. So I have a feeling 100 is not going to be crazy to compute, at least not without. We could just loop through these numbers and then we could just increment them, move them, increment them, catalog their position, and then do that for every single number. And we could just store their final positions. I mean, that doesn't seem terrible to me. I have a feeling that that's just based on how things are going to go. That's probably not going to work for part two. Can we somehow do this a different way? Can we somehow calculate? I don't know the answer to that. I don't know if we could calculate this within a specific space of geometry. I suppose maybe is the answer that we could calculate this point infinitely forward and then do some sort of like calculation, not infinitely forward, but for the total number of 100 iterations starting at 0, 4. And then we somehow know what point it's going to end at based on the variance. Like we know where it's at in the grid because we could divide by the size of the grid. Is that a possibility? And then we just do maths here. I don't know if what I'm saying is making sense, but we have a starting position. I think we could calculate that. I'm just wondering if there's a way to like shortcut it. I'm just gonna go with just calculating these actually in a loop because I think that is possible, and then we'll see what part two is. But let's first just start by parsing it. So do we know if regex is going to capture the The minus sign? I don't think it's going to. What's the, can I do this? Is that the right? Let me check. Is it? Is it the question mark after the value? What I'm doing here? Yeah, I think this is it. I suppose we should probably check not only that, but we also should check our P positions. They all look positive. Doesn't mean that they are positive in all cases, but I suppose they should be positive. Okay. Let's just go ahead and we'll make it robust enough. We'll grab this and we'll just do it in all positions here. So actually I can probably do a RE line, sound better name, dot find all string submatch. That should give me a slice of matches, and then we should be able to just stringify S here, because that's a byte. And then I don't remember what this number is here. It's the, oh, if it's less than 0, then n is the length of S plus 1. Okay, so we'll just do -1 so we get everything. And then we'll call this matches. Actually, let's just forgo that. And we'll do right. And then so for each match, because this should be a slice of string. So what do they call this? Like, what do we name this? Doesn't really matter. This is a, yeah, these are robot. So we'll call it type robot struct. And we'll call it bx, by. Okay. That's cooking. And then we will simply do robots. So list of robot. And then this is going to be robots equal 10 robots y, because that's the way I want to do it. And then we can say px is going to be match sub 1. If this was production or something like that, I would definitely be matching these. This is a little bit no fun because Yes, this is going to be 2. This is going to be Vx. It's going to be Vy. And this will also be 2. And then we can just change this to be I mean, I suppose we could just process here, but I'm going to create them just so I can have them in case I do something else with them later. What that is, I don't know, but right. So now if we do for robot, range of robots, it's how I like to write things. We're going to do our parsing first, create our objects, and then we are going to, yeah, we'll just do logros.info f, and we'll do %v, and we'll log our robot here and see. Comma. Right, and then we'll see what our output is here if we run this. All right, cool. So just kind of look at this results real quick. We've got 0, 4, 0, 4. Oh, 0, 4 should be 0, 4, 3, negative 3. What did I do wrong? Oh, this is going to be 3 and this is going to be 4. That's why. Okay. There we go. Vx, Vy, Px, Py, Vx, Vy. Yep. All right, cool. So that's done. So we've got the parsing done. So now I think if our bounds of our box are we'll call it by and bx. So bound box or bound x and bound y is going to be what is supplied here, which is (101) and 103. So that means that multiplying (101) tiles wide and 103 tiles tall. So if we deal with 0 indexing here, I actually think that's okay. Right. So is that the truth for my test? What is the bounding box for the test? (11 tiles wide and 7 tiles tall). So that's a little bit different. So let me do this. We'll call it just score, and we'll pass in the robots, which is the slice of robot, and then we'll call it the bx, by, which are ints, and we return an int. And then we can take this here, and this becomes this, and still being passed in here, which is a little bit odd for the test. I'm gonna have to do this for now. I'm not a big fan of this, but this will be fine for now. Well, we're gonna define it in global space because it's 11 and 7. But when we are here, we want bx equals 103 and by equals whatever the other number is. Let's go all the way down here. 101 and 103. So 101 and 103. And we'll worry about that kind of later because we're more focused on the test here. But in order for the test to pass, yeah. All right, so those values are parsed. So let's think about this again. I know that we can calculate this to some point out in space as a multiple of, if we just do the 3 and minus 3 times 100, that would get us to 0, 4, and let's say 300 and negative 300, right? So how do we take that and is there a way where we could calculate that in one shot per in each of these points and then automatically know what the wrapping is? So if I divide it by the x by the edge, I have the remainder, and that remainder is where it's in the final graph. Is that true? So I sort of think so. So if I do, we know we want to go for a 100 iterations. So let's just do robot dot v xv times 100 and the ny, the new y, is robot dot vy times 100. So that's our 100 loops, right? And if we do nx equal, it's robot, we'll just use r here. I'm typing robot way too much. You get the idea. Plus equal px, and then ny plus equal r dot py. So that's plus the starting point. That's where we're at in our location. And because we know we wrap, then if we say nx is the nx mod bx, is that right? And then ny equals ny mod by. So it's just the, you divide it out and then all of a sudden it's the remainder. Is that true? Let's see here. Appreciate how slow this is running. Let's see if we can get it to run every second here. So where's my test data? It's here. I'm not getting anything out my test. Why? It's because I'm not actually calling score. I don't really like how this relationship here, but I'm with the bx and by, but I'm going to ignore it for right now because I'm just trying to get this actually functioning. Okay, and then what is our actual? We still have to do the quadrants, right? But I'm not so interested in that right now. What I'm interested in is solving this first piece where each tile look like this. These robots have a unique feature for maximum bathroom security. They can teleport. Okay, so I just need to create, instead of actually looking at each one, but maybe I will look at them once. So 98 and 90 is wrong. Where is the other? Yeah, I don't care about that. Okay, so then, yeah, this is the problem. So I don't, yeah, okay, this actually needs to get moved up. This is why I don't like this, but I'm not going to rewrite everything for this right now. Okay, that's better. So 3, -2, these seem like they're relatively right, but I'm not 100% positive they are correct. Um, so let me just see here if I have like my signs flipped, or what can I do to verify like 3 and -2. So each robot is given a px where x represents the number of tiles the robot is from the left wall and y represents the number of tiles from the top wall. So that's the tile they're on. View from above. So a position of 0, 0 means the robot is all the way in the top left corner. Each robot's velocity is given with x, y, where x and y are given in the tiles per second. Position x means the robot is moving to the right, and position y means the robot is moving down. So velocity of v equals 1 minus 2 means that each second the robot moves 1 tile to the right and 2 tiles up. Okay. So -2 means 2 tiles up. Okay. Okay. I mean, that's fine, I suppose. I mean, we could. the whole like grid flipping thing is messing with me a little bit, but I don't suppose it's particularly a problem, other than if I can't articulate where we are. I think so we can't have negative numbers, or can we? If we're in a grid, right? So we have if we have a fixed set of tiles, like this here, we're never going to be at -2 position in this, right? We have a maximum set of width and a maximum set of height. And so we're not going to be at -2. We're going to be at 2, so to speak. So what do I do to flip the signs? I could do some like if negatives, then take my width -2 and take my height -2, and then that is where you're located. Maybe. So what's the final state of this grid after 100 seconds? The above example, the number of robots on each tile after 100 seconds has elapsed looks like this. So do we have anything? Doesn't quite look right now, does it? Yeah. So I did the modular, right? So I got that. I mean, this is right? I mean, Roni, I mean, we're on the right track here, I think. Um, I just have to flip these signs, right? So if nx less than 0, I'll find the right character eventually. Then nx is ex minus nx, something like that, right? Is that right? I do the same thing for ny. Something like that. 3, 2. Uh, 0, 1, 2, 3. Ah, yeah. Yep. That's a good point. We can actually I don't know why I did that. This needs to be up here. Three, 5, 5, 4, 6, 6. 0, 1, 2, 3, 1, 2, 3, 4. So the only thing is, I think that I might have my, so -2 is up. So it goes in the up direction. Velocity of -2 is up. And I think that is the only thing that is tripping me up here a little bit. I don't know if it matters exactly. One, two, three. 0, 1, 2. 1, 2, 3. 1, 2, 3. Oof. Six and 4. Let me just, I'll leave that as is. I don't really think it matters, but it might matter for the way things are visualized. So do we have anything that's in the same spot here? We've got 6 and 0. We've got 6 and 0. Let's see here. That is 2 and 2. We have 6 and 0 here. 1, 2, 3, 4, 5, 6, 7. I guess that's technically the 7th index. One, two, three, 4, 5, 6, 7. Okay. Nine and 0. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I think this is right. We're gonna leave it as this, and then I'll just split this into quadrants. So, well, first let's create our map. So if we have a map, and then we can do something like func key, keep it the same narrative here. And then we'll do something like then we'll do something like yeah, missing return. Yeah, so then we can loop through this, and we can say for, we actually want the, we don't really care about the location, so I guess I could just, subdivide them in their quadrants. Because I'm going to have to resplit out this number. Let's look at what the score is, because the score is the number of robots in each quadrant. So really, I don't really have to do a visited. I mean, I can do that. But for the first problem, it's really just, okay, what quadrant are they in? And then it's something like Q1. And then the answer for the score is, it's these multiplied, right? 1 times 3 is 3, times 4 is 12, times 1. So it really is something like that. And then so the answer is, we'll keep the visit thing here because that might come up in the second one. But it's saying that if n y greater than, do less than, should be bx it's automatically Q2 at that point, right? Because if we didn't pass this and nx is still on that quadrant, then we're at the, I guess that's technically Q3. Guess it doesn't really matter how we number them. And then if ny otherwise, or Q4, right? Something like that. Oh, I really gotta. Thanks, Go. Appreciate you. And then we want the actual to be 12. Okay. So let's go to our test real quick. Let me update the test. I realize that we're not at 12. We're at 24, and I don't know why yet. I think it's because we've got this 1 on the middle section, but that's actually, even if that was the case, that wouldn't be our problem. Oh, we're counting number of robots, so it would. So are we missing? We missing that where if it is So the problem is that we have 9, which is 4.5, which is halfway. So what row are we actually ignoring here? So it's 0, 1, 2, 3, 4, 5. So I think this might be... I think this ends up becoming 4, if I'm not mistaken, instead of 5. Because this is integer math. But I think we can do... something... Well, no, so 11 divided by 2 is... Well, I was thinking actually about 9, not 11, but... Wait a second. You're right. 1 second. Let me just reprocess that, because I remember seeing 11. The robots are in space, which is 11 tiles wide and 7 tiles tall. Okay. I don't remember why I thought about that for a second. For some reason, that was less. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5. Oh, so that actually should be fine. I don't need to do that then, because it should round down. Yeah. Okay. So then... Okay. Um... All right, so our test pass, but not the actual run. So what did I do wrong? Let's just check some of our numbers. So 101 for listen to the space, which is 101 tiles wide and 103 tiles tall. So BX 101 tiles wide and 103 tiles tall. 101, 103. That should take into effect here. And it should override this. But we could always, just to be safe, sure we're not chasing ghosts. BX 101, 103. After exactly 100 seconds have elapsed. Well, $58, $93, $51. And so $50 is right. And then 103 divided by 2 is 51. Okay. If nx is less than and ny is less than, we put it in Q1. So if both of those are true, am I missing part of the if condition here? Do we need an is that true? So that we actually have a more defined, this is the top left, if you will. This is the bottom left. And this is the top right, and this is the bottom right. Is that what I did wrong? $992. No, it's the same answer. This is not supposed to be bx. This is supposed to be by. This is supposed to be by. Okay. There we go. Awesome. All right, part 1 done. Let's go into part 2. During the bathroom break, someone notices that those robots seem awfully similar to ones built and used at the North Pole. If they're the same type of robots, they should have a hard-coded Easter egg. Very rarely, most of the robots should arrange themselves into a picture of a Christmas tree. What is the fewest number of seconds that must elapse for the robots to display the Easter egg? The what? Okay, but what does a picture of a Christmas tree look like? Like, could we elaborate a little bit more? Oh, pedantic, you're just fantastic, man. You always come in at the right time. What do you understand what this means by into a picture of a Christmas tree? Are we talking like what? You'll know it when you see it, right? Okay. So we could visualize the points, right? Um, they have a hard coded Easter egg. Okay, wait. Hold on. I think I haven't. Well, this means that my mathematical approach is not right. It works for this problem. However, okay. I'm interested to see what your thoughts were. Um, no, no. You'll know it when you see it. Yeah, okay. Yeah. So, but I didn't simulate every step is the problem, right? I went with a mathematical approach here, just kind of feeling burnt from yesterday. And here we are. So, yeah, figuring out when to stop. So printing this should actually be pretty easy for me. Let's all right, let's go with a different score here. We'll go score 2 and we'll just kind of run through it. Um and so now what we're going to do we're going to go through 100 of those, and then for each robot we're going to calculate the new position, and the new position is going to be um we'll do a okay. We'll do a slice. We'll do a grid.ins. Yeah, that's what we'll do. And then this should be a slice of int. No, we want to make All right. Well, actually, not as easy as I thought it was gonna be. I just need to fill a grid, so we're gonna do G equals to append G, and we're gonna do a make slice of int. Do we want int? No, we'll do strings. We'll do strings. Yeah, we'll do string. And the length is going to be we'll say by. Yeah, that should be it. And then that's that. Okay, now we can loop through all these. So we can say for, yeah, I think mine is too pedantic. I think because I did not like orient it to the way that it's doing things. But let's think through this. So for each iteration, right? Okay, so then we need to set, I suppose this can just be a, yeah, this needs to happen every time. And then this is just a g dot pretty is what this is. And then so and we'll just say x equal r dot oh lovely. So I have to take whatever the position currently is. Oh, okay. Yeah, so we should probably go past 100 iterations is what you're saying. Yeah, we'll come back to that. I'll just do this then for now, and we're going to I'm just going to throw them on here. I wouldn't typically do this, but again, being a little bit lazy. So we'll say cx r dot cx equal to r dot actually we don't need to add those. We don't need these actually. We'll just modify px and py in the current set. So we'll take the I index here and we'll say I dot px equal to plus equal r dot bx vy leave it in there. That'll make it easier. And then we need this rule right here. We'll keep with the ugly. And then I'm going to need some time. Second's going to take a really long time. Let's just see what we got first off. That is because and we'll go with score 2 here. And that is because this is just a string. Yep. So then we need, let's see here. Sub. That's okay. Yeah, if px is less than 0, py is greater than 0. Oh, I didn't do the modding. Where is that at? Yeah. I need to do if greater. That was a silly one. Yeah, we're getting there. I don't need to do the mod because I'm not doing the math. What I can do instead is we'll take these same things and we'll say it's greater than bx, and if it's greater than py. Is that right? Am I doing the inverse there correctly? Nope. This is by. That's why. And we'll know it when we see it, right? I didn't just see it and then totally miss it because I looked at my YouTube feed. I don't know how to unhighlight it now. So the only fear that I have is because this is a different um oh yeah, I just stopped at. Yeah, I'm definitely displaying it every second. I only went 100 iterations. Let me just do two things real quick. First off, um let me actually score this. Okay, so I went to 100 seconds just now, but I feel like this is it. I just don't feel like it's lining up the way we're expecting it to line up. Looks very close. There's a property of the thing that you do to figure out when to stop. Yeah, that isn't it. Okay, let me go for a couple more iterations then. Let me well, the other fear that I have is that this is actually not right. And so I kind of want to like switch my scoring on part 1 to make sure that I'm actually getting like all the values correct so that I know that at least we're getting to the same score. Let me copy this real quick and I'm gonna get annoyed, so I'm just gonna do and because I don't want to refactor all that. And let me take the sleep out for a second. And I should get the same score for part 1 and part 2. Part 2 is that. Which that is not end state. That is not going to be right. Anyway, this has to come from the last state. Okay. Okay. Let me just, I really do want to just validate this though. Um, yeah, we'll do. Let's at least do the test. Some like monstrous number. So, oh, because if b not equal yeah. Ah, that explains a lot. And then do that. And we'll reinitialize it every time. And that way it's there in the last iteration. And then that is 24, not 12. And that is because we are not doing the last bit of bounding, which is this. Get rid of that. That should equal or not. So are you on part 2, Greedy? So what you're supposed to do, what I'm working through right now, although I'm trying to actually what you're supposed to do is look for something in the print out of the output. So that's what I'm in the process of doing right now. I'm validating that my iteration, going away from the math solving of the problem, but my iteration approach is actually working. So if you, and I'll throw out some thanks to Pandantic. He joined at the most appropriate time. But as you can see, I'm going through each iteration of the grid here, and I'm printing out different outputs. So let me just change this to, let's say, 1,000, and let's change our timing to be like millisecond times 100 or something. Let's get a little bit faster here. Is it too fast? I definitely feel like I saw something already. What is that? I can't look at them that fast. What do you mean? Like your number was big? And what was your, just out of curiosity? Well, give me like the zeros. Like how many zeros? Pedantic, was it 10? Well, I guess Tim's was 10,403. There's one that like kind of collapses there. Interesting. So you had to wait and watch for that? But I mean, we're talking like a full Christmas tree, so would we be looking for triangles? I mean, is that essentially like what we're talking about as a Christmas tree is like literally a full tree displayed? So if I just quickly look through each iteration and only printed them out when there's like three like or like four of them closely clustered together, I mean, are we getting closer, or is it looks like it's going to spell a word here is what would be my guess, but maybe it's not the yeah. Know when I see it, but I don't want to wait the entire time. Like this is like a lot of. It's like it's trying to manifest. I don't know how to highlight it now that I've clicked on it. Whatever. Hmm. You know what would probably be better is if I wrote these iterations to a file. Um, it's a lot of data too, but I might get a better sense of just scrolling through the file than watching it on the screen here. Yeah, that's what I'm thinking. Like, we can look at less of these by having a more like, but I don't know exactly what I'm looking for here. I mean, I kind of do. It says a picture of a Christmas tree. Well, I define a Christmas tree as, you would, in the center column, you would have something, and then from that center column, you would also have something in the center, but you would have like, you could look for this plus pattern down the center column, like a Tetris, like top, middle, left, right. Okay, well, that's was 1,000 iterations. Okay, well, you said, yeah, okay. So let's look at this one real quick. You know what? I think I might be making this slightly. Let me get rid of that. I realize. Let me. Let me initialize it. And then I think we can do it like this. Instead, this is like a little inefficient, but I think it's going to make it easier for me to read it. I guess it's the same thing. It's just dots. Well, how did you get the answer faster than I did? At this point, like, did you look for a pattern, Greedy? Out of curiosity, to identify something. Yeah, I agree. It's distracting me. No, I do admit it's kind of random. Like, okay, it's like okay. Well, let's look here. Okay. Oh wait, what's this? Yeah, I think I want to look for. Yeah, I see what you're saying. So it's find the one with a similar pattern and then look at the diffs for each one. I'm exceeding my buffer. Let me look for another one with a similar pattern here. Yeah. 762. For me, um, hmm. I know I feel like you're leading me down a path here. Um, let's slow this down a little bit. 762 is 721 seconds after iteration 41. Okay. Why is 103 an interesting number? Oh, because it is the number of. Okay. Okay, but what is. Okay. Yeah, we're not gonna. We're just gonna do it this way. Um. Did I leave the sleep in there? I did. So okay, so you've got starting at iteration 41 plus 103. So not not well, it's certainly not that. Um so it should just be is that not? Um no, this is not right. Not right. I'm like right here. I just my brain's moving slow right now. So if our first iteration was at 41, 7 times 103 is 721. 103 is an interesting number. What is 144? Okay, yeah, okay. Yeah. That's what I'm thinking. Right, and then we're just gonna I'm gonna sleep between each of these iterations after we print, and we're not gonna break. And we'll mark the iteration. And we'll give it like 300 seconds. Something like that, right? You want to uncomment the sleep? Wow, it's like gonna move too fast. Here we go. Oh, look, a tree. It's an upside down tree. Yeah. So 8,178. So I don't, there's no guarantee this is my first iteration, but I think what I'll do is, yeah, I know my coordinates are they're they're wrong. Is this the middle of the board? Certainly, this isn't the first one. I mean, I feel like I've saw more than this. Yeah. Okay, I just need to like get the first one now. Um, I think what I want to do is mm, oh, you guys do think this is the first one? Okay, fair enough. No, I think I missed this earlier, is what I think happened. So if I rerun this, I just want to like search the as I'm searching through them, just print out the ones that actually matter. Um, yeah, I think it's just going by too fast. I'm too slow, which is fine. I can write it to a file or something. I mean, that's the same number I got before. All right, I was off by one. I thought it was one too low or too high, but in fact, that was one too low. Um, well, that's awesome. So I think, yeah, that was the answer. Thanks. Yeah, yeah. So, well, we did it. That was fun. Not, but a bit of a joke, but I guess a bit of an Easter egg. So in this case, actually, part one I solved with arithmetics and just went straight for the answer, thinking that maybe we were going to have a more complex problem. Instead, I got trolled by Advent of Code, and they decided that the math ways were not the ways for this one. in which case we had to iterate through them anyway. So yeah, so I think that was where I was headed, pedantic, before Tim started bringing me down this track of like using some hints about math. Um, I what I was thinking in my head, because I saw a couple of patterns that had not quite this, but I saw some things that started to manifest with like uh, spaces filled that with surrounding areas, and so I was thinking that if there was to be a Christmas tree, probably it would be centered, and so I can look at the center, I don't know, 4 or 5, and look for things that are populated, but the tree wasn't guaranteed to be filled. So I knew that that was also a flawed assumption, but it could have been another way to just only print out the things that actually matter, right? So if we were to like say, um, where's our print function? So we could say something like if um, yeah, so G sub 50 51, like we start with like not that, um, just that as an example, but maybe we could add a couple more here. So if this is not true, something like that. Expecting robots to come in a Christmas tree shape. Interesting. So why does this not work? 50, 51, 52. Our iteration mark should be, what was my number? Let's go back and look again. Kind of curious about this 8179. So if we do mm, so we know not to go past that. So then I should be able to, if G50, row 50, 51, was that not the, of course I'm going to miss printing. I really just care about printing this one. I don't need to print every other one. Yeah. So shouldn't, in this iteration of G of 50, 51, all of these should be true, right? Or am I just not thinking at the moment? Well, we could look for the pattern and then we would know on the first one that matches something in here that we exit. And then that's how we solve the problem. Alternatively, Tim, where did you get 41 from? Out of curiosity, like what was this? Just like looking through the iterations and seeing something uniquely different about 41 led to a hint that at some interval of 103, starting at 41, we would eventually meet the end. If we look at our input text, is 41 in here somewhere? Like 41's right here for x. So is this like, was this kind of like a hint here that we were starting at the 41th slide? Could we actually do that and say, okay, instead of that iteration, does that work for everybody else? Like, I realize that this is a bit goofy, but if instead of this, it is robots sub 0 dot px, and so we look at each iteration, and then this is robots, or this is, yeah, robots sub 0. Actually, no, this is the bounding x, right? Bounding y. Um, that is because no, by is 103. Okay, okay. Hmm. Oh, you know why? Yeah. Because I'm actually modifying the robot's px right now. That's why this isn't actually right. Yeah, so if I think if we turn this to ref, we would be okay. I'll call it first robot later. Okay, something's not right. I'm just wondering if we could get to the solution by using the information in each test, right? Yeah, I know we didn't know what to look for. That's fair. I'm just wondering if like the answer was there all along, and maybe if we did some like clue searching, we might have found some references other than just watching it. Yeah. Okay. Well, this was fun. Appreciate everybody hanging out. Appreciate the hints to the solution. It was a bit of a quirky one today, but it was good fun. So, thanks for hanging out and being a part of the conversation. I look forward to seeing you all not tomorrow night, but I'll see you all Sunday night. All right.